Hello everyone, this is Monica Lupion and today I will solve the example of the lecture 6 convective heat transfer correlation. So first of all, let's read the problem. Air atmospheric at a temperature of -10 Celsius flows by a vertical plate with a length of 0.2 meters. So there is a plate with a length 0.2 meters. The temperature of the air, T infinity, is equal to -10 Celsius. And the plate has a constant temperature of 30 Celsius. So T is equal to 30 Celsius. Please select the equation to calculate convective coefficient under two different conditions. One, when the air is stagnant, that means that it's a natural convection. And the second case, when the air has a velocity of 20 meters per second. 20 meters per second, so that's a forced convection. As we saw in class, we normally approach this type of problems in different steps. So first we estimate the temperature if we don't know. In this case we know the temperature, so this step is not necessary. Then we need to identify the geometry and the flow, if it's either natural or forced convection. Then calculate the Reynolds and the Grashof number, depending if it's natural convection or forced convection. Once we know the Reynolds or the Grashof number, we can estimate the value of the Nusselt number by the different correlations. Once we know the Nusselt number, it's very direct to calculate the convective heat transfer coefficient. And now, if we know the temperature, this is it. If we estimated the temperature in step number 1, we need to verify if that assumption is correct or not. And the way we do that is by verifying the Fourier second law. The heat rate over the area is equal to the convective heat transfer times delta T. If this delta T is consistent with the temperature that we estimated, then we are done. If not, we need to get back to the step number 1. Okay, so this is the general case, but as I mentioned, we already know the temperature, so we don't have to go through the step number 1 or through this interactive process. We can directly get into the step number 2, which is identification of the geometry and the flow. Okay, so let's solve the problem for the case of a plate and the natural convection first. As you remember from the presentation of the lecture, in most cases we need to evaluate the property of the fluids under the film temperature. And the film temperature, Tf, is defined as the temperature of the plate in this case, plus the T infinity over 2. So 30 minus 10 over 2, this is equal to 10 Celsius, 283 Kelvin. Okay, so and now we need to calculate the Grasov number, since we are with natural convection. The Grasov number is defined as the length, 3, the density square, the gravity, the fluid coefficient of thermal expansion, beta, delta T, over the fluid viscosity. And we need to evaluate these different properties at the film temperature of 283. So if you go to Appendix I in your textbook, you will find the values that you need. So the density is equal to 1.2614 kilogram square meter. The viscosity is equal to 1.7503 times time minus 5 Pascal per second. Thermal conductivity is equal to 24671 times 10 minus 2 watt meter and Kelvin. And this factor here is also directly indicated in the table in Appendix I. So G, beta, density, viscosity for this temperature is equal to 1.815 times 10⁸ 1 over Kelvin a cubic meter. So we have here all the elements that we need to calculate the Grasov number. So the Grasov number is equal to the length, 0.2, times the this group of numbers here, which is 0.815 10⁸ delta T, and delta T is equal to the temperature of the solid, 30, minus the temperature of the fluid, which is minus 10. And this is equal to 5.8 times 10⁷. So this is the Grasov number. If you take a look to the correlation that we need in the case of a plane with a natural convection, this correlation includes not the Grasov number, but the Rayleigh number. And this Rayleigh number depends on the Grasov number times the Prandtl number. The Grasov number we know here. Let's determine the Prandtl number. Prandtl number, the definition is the viscosity times the thermal capacity over the thermal conductivity. We know again all the information that we need. You can also find the value of the thermal capacity in the table, and this is equal to 175.03 times 10 minus 5 Pascal per second times the value of the thermal capacity, which is equal to 10057 times 10⁵ joules kilogram Kelvin over the thermal conductivity, that is equal to 4671 10 minus 2 watt meter and Kelvin. So the prime number is equal to 0.71. So now we can also include the prime number here. So the Rayleigh number is equal to 4,118,10,7. And this number is below 10.9, so this is laminar flow. Okay, so now we know that it's a laminar flow. Then if you check the slides that from the presentation of the lesson 6, you can directly use the correlation that we defined for the case of a laminar vertical plate. And that correlation is Churchill and Chu. For laminar vertical plate. And this, the definition of this correlation is that the nacelle is equal to 0.68 plus 0.670 times Rayleigh number 14 over 1 plus 0.492 over the prime number 916.49. So we have here everything we need. There is the Rayleigh number that we already calculated and the prime number as well. Doing the calculations, the nacelle is equal to 42.28. Once we know the value of the nacelle, we know there is a relationship between the nacelle and the convective heat transfer coefficient. So the nacelle is equal to H times L over the thermoconductivity. Therefore, H is equal to the nacelle times the thermoconductivity over the length. The nacelle number is 42.28. The thermoconductivity is equal to 246.71 times 10 minus watt meter Kelvin, and the length is 0.2 meters. Okay, so you do the calculations, and finally the H is equal to 521 watt square meter Kelvin. And that's the value of the convective heat transfer coefficient in case of having natural convection. Let's now solve the problem for in the case that we have forced convection. We know that the air is flowing at 20 meters per second. In the case of the first convection, we need to calculate the Reynolds number. The Reynolds number is equal to the length times the velocity times the density of the air over the viscosity. And again, we need to evaluate these different properties at the film temperature. The Reynolds number is therefore equal to 0.2 meters, which is the length, times the velocity, which is 20 meters per second, times the density of the air, 126.14 kilogram cubic meter, over the viscosity, which is 175.03 10 minus 5. And this is approximately equal to 310.5. This is higher than 245. So this is turbulent flow. If you take a look to the slides from the presentation of the lecture, you can go to the slide that indicates the correlation used for a plane surface having turbulent flow. And it's this here. The Nusselt number is equal to 0.036 times the Reynolds number, 45 times the Prandtl, 1/3. The Reynolds number is this one, is approximately 310.5, and the Prandtl number from the previous section is 0.71. You do the calculations and this is equal to 777. Therefore, the convective heat transfer coefficient is equal to the Nusselt number times the thermal conductivity over L. And this is equal to 95.8 watts square meter Kelvin. So it's higher convective heat transfer coefficient because the convection in this second case is forced. So this is natural convection and this is forced convection.